Hi, Greg Taylor here, talking about combustion and ventilation air sizing. The short version, preparing technicians to write their gas technician 2 TSSA fuel safety exam. One of the things I want to make sure that we've got straight is ensuring that we're on the same page, because there's a few different terms that are kind of close together and can be confused quite easily. So we have vent systems from appliances. The two top arrows point to vent systems on a water heater vent connector and a natural draft furnace vent connector. That's going to be in a different presentation. Okay, so the vent piping basically from the exhaust or the exit of the appliance is going to be a different presentation that we're going to go through. Combustion and ventilation air sizing is going to be the bottom four arrows, if you will. The two arrows pointing, the two middle ones are pointing to the draft hood on the natural draft furnace and the draft hood on the water heater. And the bottom two arrows are pointing to the primary and secondary or combustion air openings on the water heater and combustion air openings on the furnace itself. So the bottom four will be the ones that we'll be concentrating on. Combustion air is going to be the air that really is around the flame just after it's ignited and just before it's ignited, further divided into primary air. Primary air is about a third of the air that's required for combustion, and that is mixed with the gas before the point of ignition. So where the arrow is pointing in the actual throat of the burner itself is where the air gets introduced in, mixes with the fuel, and then goes through the burning process. The secondary air is the air inside the heat exchanger that surrounds the flame and completes the combustion process, and is accountable about 2/3 of the air supply. The secondary, 1/3 is going to be primary. The other type of air that you're going to have in a natural draft piece of equipment is going to be the dilution air, and the dilution air is going to assist in pushing that exhaust gas up through the venting system and out of the building itself. Direct vent appliances are going to have their own dedicated air supply systems coming in from air outdoors. It isn't always a high efficiency furnace like we have pictured here. It could be a tank style water heater, a tankless water heater. A lot of your room heaters now are direct vented. A lot of fireplaces are direct vented as well. So they bring all the air in they require for combustion from the outside through the snorkel, and of course the exhaust goes through its own dedicated pathway back to the outdoors. So really, because it doesn't take any air out of the building for combustion purposes, we don't have to calculate it in when we're figuring out combustion and ventilation type of air openings. The natural draft pieces of equipment here, and again, we're showing this old Lennox piece as an example, showing its draft hood, or the draft control device as it's known. 15 parts of air are going to be required for dilution, assisting those flue products going up the chimney or the vent. And the other 15 parts of air are going to be required for combustion, which of course you're going to mix with the fuel before and after the point of ignition. So those two things together, just realize that we're going to need 30 parts of air for every part of gas being burned, or every part of natural gas being burned in this piece of equipment. Now, category 3 and 4 appliances do not require dilution air because they have fans that assist pushing the air through either the heat exchanger or the vent system, or a combination of each. They don't require dilution air. So automatically, even if we're collecting the air out of the room itself, we really only have to account now for half as much air just for the combustion process. So I'm showing a mid-efficiency furnace on the left that actually has louvers in the door, so the air from the room around the furnace gets in there to supply the air for combustion. On a water heater, a power vented water heater in the middle there, right down by the gas valve, there are perforations around the skirting of the water heater, and that's where the supply air, the combustion air, I should say, enters in to that water heater. And we've even got a high efficiency furnace on the example on the right there, but what I want you to notice is that the intake pipe doesn't have a dedicated pipe heading outside. It basically is cut off and just sitting collecting the air from the room around the furnace itself. So while all three of these do not need near as much air as their old natural draft cousin, they still need half as much air. So the natural draft needed 30 cubic feet. This one's going to need, these examples would need 15 cubic feet. And again, just to reiterate what we've got here, category 1 will require 15 parts of air for combustion, 15 parts of air for dilution. They're all natural draft or gravitational type of exhausting devices. There's no fan at all incorporated in pushing the exhaust. It all happens through gravity and through hot flue gases rising. They all have draft hoods on them typically, and takes all the air for combustion and dilution from inside the building. So all of those 30 parts are coming from inside the building. Your category 2 appliances, there's no appliances currently listed that utilize category 2. And that's basically above 83% efficiency without a fan pushing those flue products through the heat exchanger. Not saying it's impossible to be done, but in today's world we find it isn't really a necessity. We typically have our higher efficiency pieces with what we call our positive fan pressure types of systems, which are going to be category 3 and 4. So category 3, 15 parts of combustion air, doesn't require dilution air, so uses half as much air. It's a fan-assisted appliance, does not have a draft control device. Only the air required for combustion comes from the inside the building itself. Now, you could have category 3. I have seen category 3 mid-efficiency furnaces that actually had a dedicated sidewall intake for air and also had an exhaust. So it's not automatically that all category 3 appliances are going to fit into this particular definition. Category 4 is going to be what we would call our traditional high efficiency with 15 parts of combustion air. We don't need dilution air. If the appliance is direct vented, as I noted a couple slides ago, you don't even have to figure it in, because any appliance that brings in all the air it requires through a dedicated piping system from the outdoors doesn't even figure into these calculations at all. If it's taking air from inside, we still have to calculate it as it is removing some of that air from indoors, and we need to size it accordingly in the proper table for combustion and ventilation air sizing. So quick and dirty combustion air sizing, a house basically is also known or called the structure in the code. So a home or the building is actually called a structure when it comes to the code. And we're going to basically break that into 2 different categories. It's going to be a loose house or a tight house. The B149.1 code defines a tight house, clause 821, as a building with A, vapor or air barrier with joints continuously sealed by taping or caulking and all thermally insulated walls, ceilings, and floors, where B has an equivalent leakage area of 78 inches squared or less at a differential pressure of 0.00145 psi, G 10 pascals as determined by a recognized Canadian fan depressurization test procedure. You'll find a lot of times TSSA will also describe close-fitting windows in some of their descriptions, which really, again, would indicate tight construction at that point. So we really need to determine whether the house that we're going to be sizing is going to be a tight house or a loose house. Homes built in the 1990s and newer are a lot of times going to be considered to be tight houses. But TSSA will say off the record that they only consider houses that have been tested for tightness and certified as being what we call R2000 tightness, applicable as far as tight houses are concerned. I would fair to say that houses built really in the 2000 century, for sure, you could pretty well deem as tight all the way down the line. Pretty well every house now is tight. So as soon as we determine a house is tight, we have to bring air for combustion in from outside. So when I say tight, you say outside. It's pretty simple. Well, we know that natural draft appliances require 30 parts of air for every room, out of the room for every part of gas being burned. Fan assists require half as much, 15 parts of air. Direct vent and sealed combustion mean the same thing, do not require any air from the room they're installed in, as they have that own dedicated system that brings the air from outside right to the appliance itself for combustion purposes. Don't get worried about the 30 and 15 number. Just keep in mind natural draft appliances need twice as much air as fan-assisted appliances. So now we have two tables. We have four tables to choose from overall: 8.1, 8.2, 8.3, 8.4. And two of those are type tables, table 8.1 and 8.2. So the difference between tables 8.3 and 8.4, even though they're both loose tables, 8.3 is for appliances that have draft control devices, or if you want to look at it this way, have natural draft appliances. Table 8.4 is going to be for appliances without draft control devices, or what we call fan-assisted appliances that are going to be in loose houses. The difference between tables 8.1 and 2, again, even though they're both tight tables, 8.1 is for appliances that have draft control devices, or natural draft. Table 8.2 is going to be for appliances without draft control devices, or fan assist appliances. So now we can narrow down which table we should use. For example, if we had a tight house with natural draft appliances, we're going to use table 8.1. If we have a tight house with fan assist appliances, table 8.2. A loose house with natural draft appliances, we use table 8.3. And a loose house with fan assist appliances, we will use table 8.4. So if we've got two appliances in a tight home, and the description in the question says we have leakage less than 78 inches squared, both appliances have draft control devices. What table are we going to use? 8.1, 8.2, 8.3, or 8.4? Well, 8.1 and 2 are going to deal with tight houses. You can see the example. We definitely have a tight house. And appliances with draft control devices are going to be found in table 8.1. So tight and draft control device, table 8.1 is going to be the one we're going to use. So where are you going to go for get your air for combustion? I say tight house, you say outside. So really at that point, all we need to do is figure out what the appliances are for the input in the space, or the appliance input is in that space. So the next question, in a structure with less than 78 inches square leakage, two appliances both with draft control devices, got a water heater at 50,000 and a furnace at 75. So table 8.1 at 125,000 BTUs per hour, appliance input burner rate, we're basically going to go to table 8.1. You're going to run down there, and I know this table might look a little different than what you have. It's an older code version that I'm using here. But really, the numbers should be the same. So 125,000 BTUs. We're going to run across here. You can see 18-inch square or 5-inch round opening. Typically, TSSA is always going to ask for a square opening size on their test question. So 125,000 BTUs would be good for 18 inches square or 5 inches round as indicated. Another thing to draw your attention to, if we have a number even a little below or even a lot below 125, let's even say that we had 102,000 BTUs combined in that space. As soon as we cross 100,000, we're going up to the 125 marker. So regardless, if it's at 101, we're going to 125. 110, we're going to 125. Until we get to 126, at which point we will then move on to 150, you're always going to move up. As soon as you cross that line, you're moving up to the next largest size. So we said we need an 18-inch square opening or 5-inch opening, and where are we going for that? For proper combustion, of course, is outside because it's a tight house. That's it. We're done. Pretty simple. Everything's going to be the same for a tight house with two fan-assisted appliances, except you're going to use table 8.2. Again, we're still going to use 125,000 BTUs per hour. And again, we're going to use table 8.2 and 125,000 BTUs. You see now, suspiciously enough, we're exactly half the size. Remember, fan-assist appliances use half as much air as their natural draft counterparts. So we had 18 inches on the loose draft hood equipped appliances. We're going to have 9 square inches on the fan-assisted appliances. The 4-inch round, you might say, okay, well, it was 5 the last time. You're going to find that because of the fact of circular and the amount of area of a circle, that number, it's not going to be like it was 5 the last time. It's going to be 2.5 inches now. It's going to be a way different equation. But your square opening will be half as much. And again, that's the one I'd really worry about in this application. So as we indicated there, 4-inch round, and of course we all knew the proper air for combustion is coming from outside because it's a tight house. And again, as I already talked about, half as much air for the fan-assist appliance. Next, we're going to do a loose house. So it was pretty easy when it came to combustion air sizing on a tight house, all you had to do, because you knew you were going outside, so it was just a matter really of calculating how many BTUs we had in that space, and then looking it up on our table to determine how big our duct has to be between the outdoors and the room that the appliances are installed in. Now with the loose house, it's going to be a little more complicated. So we now have an option on a loose house because we had construction methods that were usually, they didn't pay near as close attention to efficiency in these applications. So what they would end up doing is building walls and building the materials, basically putting things together, but not really paying a lot of attention to detail. The windows were pretty drafty, if you will, the ceiling around sills. The outdoor air barriers are nowhere near what they are today. And again, energy didn't cost that much, so it wasn't something that was really worried about back years ago. But of course, now as we tighten up that house to make it more airtight, more energy efficient, we're not going to be able to get the air of these appliances near as easily. So we have to take this into account. The loose tables give us the option of saying, okay, we don't have to necessarily have holes cut in the side of your house, bringing air in from the outside into the appliance area. In this case, we might have enough air inside the house to satisfy the requirements of those appliances. So the first option we have in loose is being able to go through and calculate out whether or not we have enough air in the house to support the combustion of the appliances that we're talking about. So the first step is going to be, we're going to go to tables 8, 3, and 4, but the first thing we have to do is figure out or calculate what the area of the home is going to be, or the whole building, or what they call the structure in the code is what we're going to figure out. So the two loose tables, 8.3 and 8.4, determined earlier. Loose house with natural draft appliances, we'll use table 8.3. If we have loose house with fan assisted appliances, we will use table 8.4. Now, as indicated, we can go ahead and figuring out that volume of the structure. So if the building does not have enough air to support the requirements of the appliances, then we'll just go right back outside like we did for the tight house. But the first step that we always want to do, because on a TSSA fuel safety exam, they want to make sure that you know how to do this procedure. If you said, oh, I'm taking it outside, that's not what they want to see. They want to know that you know how to size this accordingly. So if they indicate you're coming inside, or if you're able to go back inside for the air requirements for your appliances, that's always going to be the preferred method on a TSSA exam. So again, we're going to use the example. We have a house with greater than 78 inches squared of leakage, meaning it's loose. Two natural draft appliances, and we're going to stick with the water heater at 50,000 and the furnace at 75. The appliances are going to be installed in a home with an open basement, no doors separating the basement from the main level of the home. The dimensions are 45 by 30 feet with 2 floors each at 8-foot ceiling. So really what we need to do is we need to figure out what the volume of air inside that house is going to be, or inside that structure. So we're going to use table 8.3. We calculate the volume. It's 21,600 cubic feet of air in the house. Next, we're going to add up the inputs of the appliances. So we're going to have 125,000 BTUs. We want a table 8.3, and if you come down here on the left-hand side, you'll see the total input of the appliances combined is going to be 125,000 BTUs. We then start moving across, and when we look at 125,000 BTUs, you'll start to see the first column over has an 18 and then a 12 in brackets, right? So what we're looking at here is now we want to jump up to this top row, and if you follow my highlighter there, you'll see that we have the first column over here on the left is going to be 500. The next column is going to be 1,000, 2,000, 3, 4, 5. You get the picture, and as we start to get those increments up, until we get out here to the end, we're going to see 20,000. Remember, the slide before we calculated had north of 21,000 cubic feet of air in that house. Now, if we're in between table values, we're going to go down. So if I told you we had 19,000, you can see up here, we've got a 17.5 section on the table and a 20. If we have 19,000 cubic feet or even 19,800 cubic feet, we don't quite have 20,000 yet. So we're going to go down to that next lowest number, which in this case would be 17.5. Because we're over 20,000, we have 21,000 and change, we're going to go to the 20,000 increment at this point. We're going to come down and we're going to marry up to the 125,000 BTU line, and right beside my highlighter there, you'll see a 0. And what that tells us is we have enough air in the house to support the combustion for those appliances. So this is the first step. Now, if I gave you different dimensions and told you, again, that we didn't have enough air, so let's say I gave you house dimensions and said that, we're at 6,500 cubic feet, we'd be in between 6 and 7, so we go to 6. We come down here, and as soon as we see a number in this line, that indicates that we don't have enough air in the house. So what your option would be is to go back outside. And this number here would indicate how big our opening would have to be if we went back outside. Curiously, that 18-inch square opening is the same as the type table that we first did with appliances with draft control devices. So that opening would still have to be 18 inches square to the outdoors. So if you were doing a rectangular opening, for lack of a better way of saying it, it would be a 4.5 inch by 4 inch rectangular opening would equal your 18-inch square requirement. Now, you could go bigger. That's fine too. That's never frowned upon. But your opening size really needs to be 18 square inches according to this table. So now we're going to start on the 125,000 BTU line on the table. Move until we see the volume of the building, which is what we said the top row was 20,000. We know we're above 20,000, so we're going to choose 20,000 cubic feet of air. And you can see the point at which we intersected was 0. So we have enough air inside the house, and because there's nothing else blocking the appliances, we're done doing the calculation. And again, you can see at this point 125,000 for appliances having draft control devices, coming over here and seeing the 0 at 20,000 cubic feet of air, indicating we have enough air in that house to support the combustion. Again, this is just what I talked about before. Let's say the volume was less. It was basically where you saw a value in that table. That means we've got to go outside. There isn't enough air in the house. And again, how big would that opening be to the outside? It would be the 18 inches that we read off the table itself. Don't get hung up on the number. I want you to realize when you see the value, we can't get our combustion air from inside the house, so now we have to go back outside for appliance air requirements. And I'll tell you the reason why I tell you don't get held up in the number. A lot of technicians, as soon as they see that number, think that if I cut a hole in the wall that's 18 inches square, that I've satisfied the requirements to get the air to my appliances. It's a different rule when we go back inside the house, which we're going to talk about coming up. So you can see at this point, again, the example that I pointed out, 125, we said now we were in between 6 and 7,000 cubic feet of air, so we go down to 6,000. Because we see a number there, that just indicates we've got to go outside. How big is our opening going to be? 18 inches square to the outdoors, between the outdoors and the furnace room. So because the original question that we had said it was 21,600 cubic feet of air in a house with the dimensions 45 by 30 by 8 by 2, and we see that the intersection of 20,000 cubic feet and 125,000 BTU on table A3 gives us a 0, we're okay taking the air from inside the house because there is enough air inside the house to support the combustion of those appliances. Now, if we decided to leave it at that, we know we have enough air in the house, because there's no room or no construction around the appliances themselves, and it can communicate effectively with all of that air that's in that house, we're done. We're good to go. We don't have to do anything else. So we're going to have the exact same scenario as the one listed above, except that the appliances are now installed in a utility room in the basement of the home. So we still do everything still the same way. We got to find out, does our building have enough air, which it did. So we're good to go there. But now, because of the case, we've got to check and see how much air is there inside the room where the appliances are going to be located. So the next step is measure the enclosure volume, which is basically the room where the appliances are installed. So we're going to take the volume of the room. In this case, 8 feet by 10 feet by 8 feet. And the enclosure has 640 cubic feet. So we could actually, I pointed at 1,000 in here. We can go back to 500 at that point. That'd be the better way of going. You go down to 125, and again, you're going to get an 18 there. You'll get an 18 all the way across here for quite a few charts, or quite a few areas of the table, meaning that we've got to go, either we go back outside, because you still got that option. If you want to go outside, you can put an 18-inch opening from the outdoors right into the area where the appliances are located, or you could, because there was enough air in the house, we could actually cut an opening between the room where the appliances are installed and the rest of the house, or what the code says, have an opening between the enclosure and the rest of the structure. There's a different rule, though, that we have to follow at that point. So we know that we don't have enough air in the room, but we do have enough air in the house itself. So what size must these openings be? Well, Code Clause 826 indicates, I'll cut to the chase, the rule is basically when we're going back inside between the enclosure, the room where the appliances are located, and the structure, the rest of the house, we need an opening size now of 1 square inch for every 1,000 BTUs of firing rate in that room. So we have 125,000 BTUs in the room. This is pretty simple. Knock the 3 zeros off, and that gives you the size of the opening that we need between the room and the rest of the house, or between the enclosure and the structure, to satisfy the air requirements for this piece of equipment, or pieces of equipment, as we have in this case, between the water heater and the furnace. So we said we've got 125,000 BTUs of firing rate. Each opening is going to be 125 square inches at that point. If any appliance in that room or enclosure has a draft control device or is natural draft, we'll require 2 openings that will both be the same size. So ultimately, you're always going to figure out the lower opening size using mathematics. In other words, 1 square inch for every 1,000 BTUs is going to give you your lower opening size. Under 400,000 BTUs, the code dictates if we need a second higher opening, it's going to be the same size as the lower opening that you just calculated. So we know at this point, because we have natural draft appliances, both of them are natural draft, but it wouldn't even matter if it's just one. If we have any natural draft appliance in that room, we need 2 openings the same size. In this case, they'd be 125 square inches in size each. The upper opening will be as high in the wall as we can possibly get it, but never lower than the lowest draft hood in the room. The lower opening always has to be between 6 and 18 inches off the floor. If no appliances have draft hoods in the room, then the lower opening is the only one that's required. As soon as we have any draft hoods, as I mentioned, 2 openings, both the same size. So really, that's it. We're done that one too. Of course, loose fan assisted would be done the exact same way, only using a different table. Now, if they're both fan assisted in that room, we only need 1 opening, right? We'd only need 125 square inch opening between 6 and 18 inches. So they call the lower opening the combustion air opening. They call the upper opening, when you have draft hoods, a ventilation air opening. So we're going to use the example, have a house greater than 78 inches square to leakage, 2 fan assist appliances, water heater at 50,000, a furnace at 75. Again, the appliances are installed in an open basement with no door separating the levels. You do the math, again, we're back to 21,600 cubic feet of air. And again, we're going to use 125,000 BTUs, but this time on table 8.4, because both appliances have no draft control devices. So when you look across here, you can see we get up to 20,000, and again, we've got a dash indicating that we have more than enough air to satisfy the requirements from inside that home. So indicating there, either a dash or no number at all, indicates there's enough air to support combustion for the appliances. So we have enough air in the house. So as long as that's all we're doing, we're done. We don't have to do anything else to satisfy the air requirements for these pieces of equipment. And again, showing a slide with the same numbers. If the house had a volume of 3,700 cubic feet, we would use the 3,000 cubic foot air volume column on A4 because, again, we're always going to do worst case scenario, which is less air. So two tables like 3,000 and 4,000, the worst case scenario is going to be to have less air. So we're going back to 3,000 cubic feet of air is the volume that we're going to choose for this example. So we look at the intersection of 3,000 cubic feet and 125,000 BTUs of appliance input, and you're going to see the circle numbered in red on table A4 in the next page, and it should indicate 9, meaning that if we could go back outside for air, and if there isn't enough air inside the house, we are going back outside for air, and that opening is going to be 9 square inches, so a 3x3 opening to the outside. And again, you can see at 125,000 BTUs, we run across here to 3,000 cubic feet of air in the house, and we see a response here of 9 square inch opening size. So we go back to the original question. We got 21,600 cubic feet of air, 45 by 30 by 8 by 2. Comfortable at the intersection 125 to 20,000 cubic feet. We have a dash, so we can continue taking the required appliance combustion air again from inside the house. And again, in an open basement, so really our work is done. In an open basement, we have enough air to satisfy the requirements for those appliances. Again, you could see looking across the table, 125,000 BTU, and matching it up at 20,000, and you see a dash there indicating that there's enough air in the house. The last kink, again, same as above, only installed in the utility room. Same thing, same question. Still going to be 125,000. Volume of the house is still going to be just over 21,600 cubic feet. We still have enough volume in the air to support the requirements, or volume in the house to support the air requirements. So now we're going to install those in a room, check to see if the room has enough air to support combustion. Again, 8 by 10 by 8. Again, we're going to go onto the table, and you're going to see at 500, we see 9. As soon as we see a numeral there, that means we don't have enough air in the house. We got to go outside. Now, we do have enough air in the entire house. We already measured that. So now with one option, we could either go outside, or we can knock that hole back in between the enclosure or the room and the structure or the building. That hole isn't going to be 9 inches if you're doing that. Keep in mind, again, 1 square inch for every 1,000 BTUs, so we're going to need an opening 125 inches squared. So what we're indicating here is we could cut a hole. Now, keep in mind, we only need one because both appliances had fan assists on them. So no draft hoods in that space, so we don't need to put 2 holes in the wall. Only the lower opening would be all that's required by code. And it'd be 125 square inches at that point. So again, the size, basically, you could go back to 826, and it's going to indicate 1 square inch of opening size for every 1,000 BTUs of firing rate. We have 125,000 BTUs, so we just knock off the 3 zeros. Our opening needs to be 125 square inches. So the opening at that point would be 125 as indicated. If the appliance in the room or enclosure has any draft control device that require 2 openings at 125 square inches each, the upper opening as high in the wall as we can get it, but never lower than the lowest draft hood. The lower opening between 6 and 18 inches off the floor. In this case, no appliances had any draft hoods, so we only need the lower opening in this case. So Shazam, we're done that one too. One of the things that I also want to talk about, a lot of times you stick a hole in somebody's wall, depending on where that hole is. Maybe it's into a nice finished rec room that they entertain in, or maybe a nice area where the family gathers, and they don't want to have this ugly hole protruding. So a lot of times we'll put a grill over the hole just as a decorative piece. It still allows air to travel back and forth, but it just looks more appealing than a hole sitting in the wall. A lot of times that grill that we're going to put on is going to take away from some of the area of air that can transmit back and forth from one room to the other. So manufacturers will typically have that information either available on a website in their information package. The wholesaler might be able to get the information for you, or it might even be on the wrapper of the grill itself to indicate what they call free area of the grill. And on a TSSA fuel safety exam, they've got to give you free area of the grill because you obviously physically aren't going to have a grill to measure to see. But really, what happens here is we know that our opening size is 125 inches, and I'm going to talk this through here a little bit as we go. We're going to divide the opening size by the grill free area to obtain your new opening size. I'm trying to remember whether I put it on the slide here or not. No, I didn't. So just to kind of carry on that last slide, if we knew our opening size is 125 inches squared, right, for that application, and we had, let's say, a 60% free grill area, free area grill, 125, you need to divide it by 0.6. If you multiply, you will get a wrong answer, trust me. So you're going to take 125, and in this case, if it's a 60% free area grill, we would divide by 0.6. Our new opening size is going to be 208.333 inches. So in order to get 125 square inches of air through that grill, our opening now needs to be 208.333 inches squared. I just want to make sure that you understand how to do that, because our friends at TSSA do like sticking at least one of those questions on there with a grill size on it and telling you to calculate it. The next piece here is above 400,000 BTUs. The great thing about this, everything is outdoors. There's no more, are we going outside? Nope, it's all outdoors. So it splits the appliances again into two categories. And keep in mind, they don't have to be above 400,000 BTUs to get in this mode. We could have three 200,000 BTU appliances equal 600,000, but if they're in the same room, the rules above 400,000 BTUs kick in. So we're going to split the appliances into two categories, those that have draft hoods, and those are what they call power burner appliances. So appliances with draft hoods, all of these inputs are going to be added together to get a total. Then we're going to divide the first million of that input by 7,000. If we had a 600,000 BTU boiler, that's all that was in there, we're going to divide that 600,000 by 7,000. If we have, in this case, I think we've got an example coming up, which I'll talk about. All of the inputs above the initial million are going to be divided by 14,000 to determine the combustion air opening size. The ventilation air opening size, or that upper size, remember, under 400,000, we said they were going to be the same size. They were both 125 square inch openings. When it comes to above 400,000, you're going to calculate the lower combustion air opening size. Your ventilation air opening will be 10% of the combustion air opening size. So we're going to talk a little bit about more of that coming up. So in this case, we have 2 million BTU per hour draft hood equipped boilers in a mechanical room. So if we are going ahead to properly size this, remember, 4 million BTUs is our total. We've got the first million divided by 7,000, which equals 142.86 inches squared. The remaining 3 million would be divided by 14,000, which equals 214.29 inches squared. And adding those two numbers together are going to equal 357.15 inches squared. So the combustion air opening coming into that boiler room is going to be 357.15 inches squared, or if we went 36 by 10, would be 360 inches squared. So a 10-inch wide opening, 36 inches long would be acceptable in this case. The ventilation air opening size is going to be 10% of that 357.15 we calculated for combustion air. So pretty simply, I just moved the decimal place over once I've done the calculation for the combustion air size over one spot to the left. And you can see that 357.15, 10% of that is going to be 35.715 inches squared. So the upper opening will be 35.715 inches squared. So a 4 by 10 would work to equal 40 inches squared. Now we're going to look at the power burning appliances. When we look at those appliances, the rule, we have to have the total input of the power burner appliances added together, and everything basically is going to get divided by 30,000. So your power burner appliances, we take the entire input, 4 million, divided by 30,000, equaling 133.33 inches squared, and our ventilation air opening would be 10% of that, so 13.33 inches squared. The big thing to keep in mind, that ventilation air opening size can never go less than 10 square inches. There's a trick question a lot of times on the test that indicates a number lower than 10, because your combustion air opening size is, let's say, 70 inches. So of course 10% of that would be 7 inches. You have to keep in mind that the minimum opening size for your ventilation air is going to be 10 inches. That's in the code. So now we combine those two together. What we do is do them separately. So we have two 2 million BTU per hour draft hood equipped boilers and two 2 million BTU power burner boilers in the same mechanical room. We're going to figure them out separately and then combine the sizes at the end. So your first step, you're going to take your two 2 million natural draft boilers, the first million divided by 7,000, which is 142.86. The remaining 3 million is going to be divided by 14,000 to give you a total of 214.29 inches squared. So adding those together brings us a total of 357.15 inches squared opening for these two boilers. Two 2 million BTU power burner boilers takes the whole input, 4 million BTUs per hour, divided by 30,000, which is going to equal 133.33 inches squared. Now that we have both of those, we can add those two numbers together to come up with our grand total opening size, which in this case, 357.15 inches plus 133.33 inches squared is going to equal 490.48 inches squared. So your ventilation and air opening size will be 10% of that, so 49.048 inches squared. So that's it for combustion air sizing. Hopefully this is an exercise that will really help you through and hopefully be able to assist you in properly getting your practice ready for your TSSA fuel safety exam. Again, Greg Taylor from HVAC Training Academy signing off.